On December 26, 1990, a 5.8 magnitude earthquake tore through southeast Sicily. Modern reinforced concrete buildings pancaked. Steel-framed structures twisted. But in the hilltop town of Noto, the Baroque cathedral, built in 1776 using medieval construction principles, stood firm. 20 meters away, a 1960s apartment complex crumbled into rubble. The cathedral's walls, held together with lime mortar and built using techniques passed down from the 1200s, flexed and absorbed the shock. The concrete building, engineered with modern seismic codes, couldn't handle the lateral forces. Engineers spent months studying why the old building survived while the new one failed. What they found challenged everything they thought they knew about earthquake-resistant construction. Medieval builders never heard of seismic engineering or wind load calculations. They couldn't model stress distribution on computers or test materials in labs. Yet their structures regularly survive disasters that flatten modern buildings. The Hagia Sophia in Istanbul has weathered dozens of major earthquakes since 537 AD. The half-timbered houses of Germany bend in hurricanes that would shatter conventional framing. Stone bridges built in the 1300s carry loads their builders never imagined, while modern bridges need replacement every 50 years. These weren't accidents. Medieval masons developed specific techniques through centuries of trial, error, and careful observation. Then, we forgot most of them. Flexible mortars. Modern concrete sets hard. That's the point. Engineers want rigid connections that transfer loads predictably from one element to another. Medieval builders wanted the opposite. They mixed lime mortar, a paste of slaked lime, sand, and water that stays slightly flexible even after it cures. When an earthquake hits or a building settles, lime mortar compresses and shifts without cracking. The mortar acts like a cushion between stones, absorbing movement instead of transmitting it. The Cathedral of Santa Maria del Fiore in Florence, completed in 1436, uses lime mortar throughout its massive dome. Engineers studying the structure in 2012 found that the mortar joints actually compress during seismic events, allowing the stones to shift microscopically without losing contact. Portland cement, invented in 1824 and now universal in construction, doesn't do this. Cement mortars are stronger than the stones they connect, which sounds good until you realize this means the stones crack instead of the joints. In a 2015 study published in Construction and Building Materials, researchers tested medieval lime mortars from structures in Italy and found they maintained 40% flexibility even after 700 years. Modern cement mortars lose all flexibility within months of curing. Medieval masons also understood that different parts of a building move differently. They used weaker mortars at the base where settling occurs and slightly stronger mixes higher up. The Alhambra in Granada, built between 1238 and 1358, employs 5 different lime mortar formulations in different sections. Ground-penetrating radar studies in 2008 revealed that the foundation mortar contains more sand and less lime, making it softer and more compressible. The mortar in the upper walls has more lime, providing better weather resistance. This graduated approach lets each part of the building respond to stress in its own way, instead of forcing the entire structure to act as a rigid unit. Interlocking without cement. The Inca citadel of Machu Picchu, built around 1450 using techniques that mirror medieval European practices, contains walls of stones so precisely cut they fit together without any mortar at all. When the 2007 earthquake hit Peru with a magnitude of 8.0, these dry-stacked walls danced, literally. High-speed cameras captured the stones shifting against each other, absorbing the seismic waves, then settling back into place. Not a single wall collapsed. Modern buildings in nearby towns, constructed with conventional mortar and rebar, crumbled into piles of broken concrete. Medieval European builders used a similar approach called ashlar masonry. Instead of relying on mortar to hold stones in place, they cut each stone with slight irregularities and projections that locked into the neighboring stones. The technique requires incredible precision. Masons spent days shaping individual blocks to ensure they nested perfectly. The investment paid off. Canterbury Cathedral, built starting in 1070, uses interlocking ashlar in its foundations and lower walls. Ground-penetrating radar surveys in 2016 showed that many of the stones have shifted up to 3 centimeters over the centuries, yet the walls remain plumb and stable. The interlocking shapes prevent the stones from sliding out of alignment even as the building settles and moves. The physics here contradicts modern engineering intuition. We're taught that stronger connections create stronger structures. Medieval builders proved that strategic weakness creates resilience. When stones can move slightly relative to each other, they distribute stress across the entire wall, instead of concentrating it at rigid connection points. A 2019 study by researchers at the University of Minho in Portugal tested dry-stacked stone walls against mortared walls in simulated earthquake conditions. The dry-stacked walls withstood 30% more lateral force before failing, and when they did fail, they disassembled rather than shattering, making them easier to repair. Timber frames. That bend half-timbered houses dot the German countryside, their exposed wooden frames filled with wattle and daub or brick. These structures look quaint, but they're engineering marvels. The frames use mortise and tenon joints secured with wooden pegs instead of nails or metal fasteners. When wind or seismic forces hit the building, the wooden joints compress and rotate slightly, allowing the entire frame to flex. A study published in Engineering Structures in 2017 found that traditional timber frames can deflect up to 10 degrees from vertical without structural damage. Modern rigid frames fail at deflections of 2 to 3 degrees. The secret lies in the joints. Medieval carpenters cut mortises, holes, slightly larger than the tenons, projections, that fit into them. This intentional sloppiness creates play in the connection. When the building experiences lateral forces, the tenons can rotate within the mortises, dissipating energy through friction. The wooden pegs that secure the joints also compress and deform, acting as shock absorbers. After the stress passes, the frame springs back to its original position. This same principle appears in Japanese temple construction, where massive timber buildings survive in one of the most earthquake-prone regions on Earth. The Goslar Imperial Palace in Germany, built in the 11th century, includes timber roof trusses that have flexed through 1,000 years of storms. Laser scanning in 2014 revealed that the joints show wear patterns consistent with repeated movement, yet the structure remains sound. Engineers calculated that if the same building were constructed with rigid steel connections, the frame would have failed centuries ago from metal fatigue. Wood forgives repeated stress in ways that metal and concrete cannot. Base isolation before science. Modern earthquake engineering uses base isolation, mounting buildings on flexible bearings or sliders that let the structure move independently from ground motion. Medieval builders achieved the same effect without the technology. They built on layers of different materials that could slip and compress during seismic events, effectively decoupling the building from the ground. The Basilica of San Francesco in Assisi, constructed starting in 1228, sits on a foundation of loose stone rubble topped with compacted earth, then wooden planks, then more rubble, and finally the dressed stone foundation walls. This sandwich of materials creates interfaces where slippage can occur. When the 1997 Umbria March earthquake struck with magnitudes up to 6.0, the basilica suffered damage, but analysis showed the foundation layers had compressed and shifted, absorbing much of the seismic energy before it reached the walls. Modern buildings in the same area, constructed directly on concrete slabs anchored to bedrock, experienced more severe structural damage despite being built to contemporary seismic codes. The technique appears across medieval architecture in earthquake-prone regions. The Hagia Sophia in Istanbul, completed in 537 AD, rests on a foundation of stepped layers of brick and stone with clay mortar between them. Engineers studying the structure using ground-penetrating radar found that these layers have compacted unevenly over the centuries, with the clay mortar acting as a sacrificial cushion that crushes during earthquakes instead of transmitting forces to the superstructure. The building has survived at least 30 significant earthquakes that would have destroyed a conventionally founded modern building. Curved walls and domes. Medieval builders loved domes and vaulted ceilings, and not just for aesthetic reasons. Curved structures distribute loads in ways that flat surfaces cannot. A dome transfers weight downward and outward in a continuous path of compression. There are no tension forces pulling the structure apart, no weak points where stress concentrates. This makes domed structures incredibly resistant to all types of forces, including earthquakes and wind. The Pantheon in Rome, completed in 126 AD but using techniques medieval builders would later perfect, remains the world's largest unreinforced concrete dome at 43 meters in diameter. It has survived nearly 2,000 years of earthquakes, including several that damaged or destroyed neighboring buildings. The dome's curvature creates a structure that gets stronger as loads increase. When seismic waves hit the building, the dome flexes as a complete unit, rather than breaking into separate failing components. Medieval masons took this principle further with pointed arches and ribbed vaults. The pointed arch, perfected in Gothic architecture, directs forces more efficiently than a semicircular Roman arch, allowing builders to span larger distances with less material. The ribbed vault, where intersecting arched ribs support thin stone panels, creates a structural system that's both lighter and more flexible than solid barrel vaults. The Cathedral of Notre Dame in Paris, built starting in 1163, uses ribbed vaults throughout. When fire severely damaged the cathedral in 2019, engineers found that the medieval vaulting system, despite being exposed to extreme heat, maintained its structural integrity because the ribs continued to carry loads even as individual stone panels cracked. Buttressing and load paths. Flying buttresses look decorative, but they're sophisticated engineering devices that redirect lateral forces down to the ground through exterior supports. Gothic cathedrals pushed wall heights to extremes while filling those walls with huge stained glass windows. This required moving the load-bearing function outside the walls to the buttresses. The buttressing system at Chartres Cathedral, built between 1194 and 1220, includes multiple tiers of flying buttresses that catch the lateral thrust from the roof vaults at different heights. Wind tunnel testing in 2011 showed that the buttresses also help manage wind loads, channeling air around the building and reducing pressure on the walls. The system is so effective that the walls themselves carry almost no lateral load, making them essentially non-structural. In modern terms, the cathedral uses a complete exoskeleton. This approach has proven more durable than conventional modern construction, where walls perform multiple structural functions and failure of one element can compromise the entire building. The buttressing principle extends to fortification walls. Medieval castle walls often feature regular buttress projections that break up the wall plane and prevent progressive collapse. When a section of wall fails, the buttresses compartmentalize the damage instead of letting it propagate. The walls of Carcassonne in France, restored in the 19th century but originally built in medieval times, show this clearly. The outer wall includes massive buttresses every few meters. Historical records show that when sections of wall were damaged by siege weapons, the buttresses prevented the collapse from spreading, allowing defenders to quickly repair the breach. Water management as structure. Medieval builders obsessed over water. They understood that water infiltration causes more long-term damage than storms or earthquakes. Their solutions were structural rather than just protective, integrating water management into the building's form. Stone walls in medieval buildings are typically built with 3 layers, 2 faces of dressed stone and a rubble core. The faces shed water quickly because they're made of tight-fitting, non-absorbent stone. The rubble core, filled with smaller stones and mortar, allows some water penetration but provides drainage paths that move water down and out through weep holes at the base. This system prevents water from accumulating in the wall, where freeze-thaw cycles would cause spalling and deterioration. The roof systems show even more sophistication. Medieval steep-pitched roofs, often dismissed today as purely aesthetic, serve critical structural functions. The steep pitch, typically 45 to 60 degrees, sheds water instantly, preventing saturation of the roofing materials. The large overhangs protect walls from direct rain impact, and the roof structure itself, with its exposed rafters and trusses, allows air circulation that prevents condensation and rot. The Cathedral of Salisbury in England, completed in 1258, features a drainage system that includes gargoyles, not just decorative but functional waterspouts, internal channels in the walls, and underground drains that move water away from the foundation. A 2018 study using thermal imaging found that the system still functions perfectly after 760 years, keeping the walls dry even during heavy storms. Modern buildings with their complex vapor barriers and flashing systems often experience moisture problems within decades because they try to completely seal the building envelope. Medieval buildings work with water, providing pathways for it to enter and exit without causing damage. Stone corbelling and cantilevers, medieval masons built corbelled structures by projecting each course of stone slightly beyond the one below it, creating overhangs, balconies, and even complete additional floors without internal supports. This technique requires precise understanding of load distribution and the properties of stone. Stokesay Castle in Shropshire, England, built in the 13th century, features a timber-framed upper story that projects nearly a meter beyond the stone lower walls, supported entirely by stone corbels. Engineers studying the structure calculated that the corbels work because they redirect the vertical load from the overhanging floor into the wall at an angle that follows the stone's natural grain structure, preventing it from cleaving. The technique also creates a self-tightening system where the weight of the overhang compresses the corbels against the wall, actually strengthening the connection over time. Corbelling appears in bridges as well. Many medieval stone bridges use corbelled approaches, where the road surface gradually widens as it reaches the riverbank, distributing traffic loads over a larger foundation area. The Pont Valentre in Cahors, France, completed in 1355, employs this technique. Structural analysis shows that the corbelled approaches help the bridge handle modern truck traffic that weighs 50 times more than medieval carts, because the load spreading effect compensates for the increased weight. Rammed earth mass. Earth construction seems primitive, but medieval builders developed rammed earth techniques that create structures as durable as stone. Rammed earth walls, built by compressing layers of damp earth in wooden forms, create massive thermal mass that stabilizes temperature and resists both wind and seismic forces through sheer weight and density. The technique requires specific soil composition, about 30% clay for binding, 70% sand, and gravel for stability. Too much clay, and the wall cracks as it dries. Too little, and it doesn't hold together. Medieval builders tested soil by feel and sight, achieving results that modern engineers struggle to replicate even with laboratory analysis. The Alhambra in Granada includes extensive rammed earth walls, some nearly a meter thick. Core samples taken in 2010 showed the earth had compressed over time to a density approaching that of soft stone. The walls have survived 7 centuries of earthquakes, including several magnitude 6+ events. The mass of the walls provides damping that absorbs seismic energy, while their monolithic construction prevents the kind of joint failures that plague masonry buildings. Modern rammed earth construction, popular in sustainable architecture, often uses cement stabilization, which makes the walls stronger initially, but also more brittle and prone to cracking. Medieval builders relied on proper compaction and composition instead of chemical stabilizers. Cruck frame leverage Cruck construction uses pairs of massive curved timbers that extend from ground to roof peak, forming both walls and roof structure in a single bent unit. This creates a building that acts as an integrated structural shell rather than separate wall and roof systems. The curved crucks, typically cut from naturally curved trees, direct loads through compression along the timber's grain. This is crucial because wood is much stronger in compression along the grain than in tension or bending across it. The crucks lean inward at the top, creating a stable triangular form that's self-supporting. Multiple cruck bents spaced along the building's length are connected by horizontal purlins, creating a structure that distributes loads three-dimensionally. Weald and Downland Living Museum in England has documented over 200 cruck-framed buildings, some dating to the 13th century. Structural testing on one 14th century cruck barn showed the timber still retained 85% of its original strength after 600 years. The cruck frames have bent and deformed over time but never failed catastrophically. Modern stick-framed buildings, where walls and roof are separate systems connected by problematic connections, regularly fail when those connections corrode or pull apart. Cruck buildings can't fail this way because wall and roof are continuous. Arch action in openings. Medieval masons cut openings in walls using arches rather than lintels. This simple choice has profound structural implications. A lintel, a horizontal beam spanning an opening, experiences tension forces on its bottom face. Stone is terrible in tension, so stone lintels must be massive and still frequently crack. An arch converts the loads into compression forces that spiral down the arch's curve to the supporting piers. Stone excels in compression, so arches can span wider openings with less material. The principle extends to structural stability during disasters. When an earthquake or explosion damages a building, linteled openings become weak points, where walls tend to separate and collapse. Arched openings maintain their integrity because the arch stones lock together under compression, actually becoming stronger when loads increase. The Abbey of Cluny in France, largely destroyed during the French Revolution, but originally built starting in 1088, featured windows and doors, exclusively with stone arches. Remaining sections show that even where walls have partially collapsed, the arched openings remain intact. Engineers studying the ruins found that the arch stones, despite being dislodged from their original positions, stayed locked together in compression, even as the surrounding wall material crumbled. Medieval builders also discovered that slightly pointed arches are more efficient than semicircular ones. The pointed arch directs loads more steeply downward, reducing lateral thrust on the supporting walls. This allowed Gothic builders to pierce walls with enormous windows without compromising stability. The principle is so sound that modern engineers now use pointed arches in tunnel construction and other applications where minimizing lateral forces is critical. Foundation grading. Medieval builders couldn't excavate massive foundation trenches or pour concrete foundation walls. Instead, they used stepped foundations that distributed building loads over larger soil areas while minimizing excavation depth. The technique also creates multiple planes of shear resistance that anchor the building against sliding during earthquakes. A typical medieval foundation starts with a trench dug to undisturbed soil, filled with large stones set without mortar. These drainage stones prevent water from pooling under the building. Above this comes a layer of rubble and lime mortar, wider than the wall above. Then another layer, slightly narrower. This stepping continues upward until the foundation reaches ground level at the same width as the wall. The result is an inverted pyramid that distributes the building's weight over an area much larger than the wall's footprint. Excavations at York Minster revealed foundations built this way between 1220 and 1472. Despite the building's enormous size and weight, the central tower alone weighs over 16,000 tons. Differential settlement has been minimal. Surveys using laser scanning show the building has settled less than 10 centimeters in 800 years, and that settlement has been uniform enough to avoid structural stress. Modern buildings on similar soil typically experience several centimeters of settlement in their first decade, often unevenly, causing cracking and structural problems. Conclusion: medieval builders worked without computers, without steel reinforcement, without the ability to calculate loads or model structural behavior. They compensated with deep observation, careful documentation, and willingness to learn from both successes and failures. The techniques they developed rely on fundamental physical principles, materials that can absorb energy that would otherwise cause failure. Structures that distribute loads along natural pathways last longer than those that fight against material properties. Buildings that work with environmental forces like water and wind survive better than those that try to resist them completely. These aren't historical curiosities. Modern engineers now study medieval structures to solve contemporary problems. Seismic retrofit of historic buildings has taught us that adding flexibility often works better than adding strength. Research into lime mortars has shown they outperform cement in specific applications despite being weaker. Analysis of timber framing has influenced modern wood construction codes. The principles remain sound even if the specific techniques need adaptation. The irony is that we abandoned these methods not because they failed, but because they required skilled labor and patience. Lime mortar takes months to cure fully. Cutting interlocking stones takes days per stone. Modern construction prioritizes speed and reduced labor costs, even if the results last a fraction as long. Medieval buildings still standing after 800 years suggest that maybe speed isn't the only metric that matters. When the next earthquake or storm hits, the old buildings might again prove more resilient than the new ones, not through luck, but through principles their builders understood without ever needing to calculate them. If you found these forgotten techniques valuable, hit the like button and subscribe to Medieval Over Modern for more discoveries about what we lost when we stopped looking backward. Drop a comment and let me know which technique surprised you most, or if you've seen any of these methods still being used today. Share this with anyone interested in construction, survival, or just understanding why the old ways sometimes worked better than what replaced them.